Today's lecture is in memory of the late Maarten de Wit, founding director of E.ON and a collaborator and friend over 2 decades. I would like to acknowledge and welcome our Vice Chancellor, Professor Sibongile Mutwa. The Nelson Mandela University conferred the title of Emeritus Professor to Maarten posthumously, and this was a first at the university. Thank you, Vice Chancellor. I would like to also acknowledge the family of Maarten de Wit, in particular his life partner Lynn, daughter Tandy, and son Chart, who will be watching this lecture. I wish to thank everyone who is joining us today for your time and participation. Our special guest today and presenter of his first memorial lecture in honor of Maarten is Emeritus Professor Brian Horsfield, a close friend of Maarten. Together, Maarten and Brian run the Inkaba Africa flagship research initiative between South Africa and Germany for studying Earth as a planet from core to space. This was in 2004 already, with the aim to bring together cutting-edge research and capacity building. Now, a few words about Prof Horsfield. He is an elected member of the German Academy of Science and Technology, Emeritus Professor of Organic Geochemistry and Hydrocarbon Systems at the Technical University of Berlin. And he is Senior Scientific Advisor to the German Research Center for Geosciences in Potsdam, known as GEOS4. Brian Horsfield holds honorary and professorships at universities in Australia and China. He's co-founder and CEO of GEOS4 GmbH, a research and service provider for the energy sector. He has about 300 publications to his name. I now invite Emeritus Professor Brian Horsfield to present his lecture.
So, good afternoon, ladies and gentlemen. Welcome to my dining room. It's a real honor to be presenting a talk here on the first anniversary of Maarten's passing. It's not ideal, but this is the best we can do under the current circumstances. Thank you for actually showing up to listen to my talk today. It'll last about 40 minutes, I think. Hopefully you have the patience to hang around. A few words maybe at the very beginning about Maarten. Most of you know Maarten, so you know how enthusiastic he was, that it was contagious, a contagious feeling, this enthusiasm that he had, especially towards the training, the tutoring of young people. He was a real inspiration, not only to the youth of South Africa, but to all of us who actually had the privilege of working with him. He was a great guy, he was fun. And it's always fun if the science is good and the person is a good guy. And that applied to Maarten. What I'll do now is to switch over to my talk, which, as I've already mentioned, it should last about 40 minutes. Let's do a click over. Hopefully the first slide now is showing. It's a simple slide. It's my name and the title of the lecture. Let's get to the real content now. This is me standing next to Maarten in 2003 in Potsdam. It's where we first met. I'm not going to give a whole history of our lives together. This is just where we met. We ran a project called Inkaba Africa. And as the cartoon shows, this is a big holistic study from core to space, examining the natural phenomena of Earth. We had leading technology to help us do that, and it did provide fundamental insights into the workings of the planet. Our motto was think big, and you can't get bigger as an Earth scientist than the whole Earth. So that's what we did. Was it a success? It was. Big bucks, big science output, big capacity building statistics. On this slide, you can see top left, all the institutions that were involved from South Africa and Germany. 24 million euros in phase one. Ships, staff, stuff, pictures of those three things are shown there. What kind of output? These were to do with three research themes that covered everything from the core up to the surface and out to the margins of South Africa. Right, so going even a little bit further back, 2002, Cape Town. That's where we first met up as scientific groups to basically check each other out. Could we actually work together? It did work out. You'll see here that I gave a talk at that meeting. Natural gas generation from deep hot basins to bacteria was the title of the talk. So I've chosen a similar title for today, just for continuity's sake. This is another reason for talking about natural gas. This is a picture of Maarten and I at a shale gas workshop, think tank, back in 2012. Both of us have been dragged in, partly kicking, into not scientific debates, but political debates about shale gas. And I'll get into some of those details later in the talk. But this is why I'm actually talking about natural gas today. So the official title of the talk, Peddling the Methane or Methane Cycle. Bit of a strange title, I admit. Sounds a bit like a bike that's somehow made out of gas, obviously nonsense. In fact, many of you will already know that peddling can also mean to try to get people to accept or to believe something. It could be science or it could be politics. And here we have a peddler, the person who's trying to sell stuff. So in my talk today, I'll be talking about peddling, the methane cycle. And by the methane or methane cycle, I'm referring to the formation and occurrence of methane in Earth's sedimentary basins. I'm not going to be touching upon primordial gases. Right. So thank yous are extended here to three people in particular: Hans-Martin Schulz and Sarah Gleason of GFZ in Potsdam, and Barry Morkel down at NMMU in South Africa. They provided me with some of the slide material that I'll be showing. Okay, let's move on here. Challenging start to the talk here. This is a structural image of methane. CH4, the simplest organic molecule. One carbon atom bound to 4 hydrogen atoms. This slide shows sedimentary organic matter, or examples of it. Bottom right, methane again, the simplest organic compound of all. Above it, we have an organic compound that's made out of more than 27 carbon atoms. This is actually an example of something that is found in biological materials. These are steroidal compounds. We find them in sediments from the remains of dead organic matter that found its way into the sediment. Jump over to the left and you'll see that organic matter is visible down a microscope too. You don't have to be a chemist to mess around with organic matter. Top left, you'll see brightly fluorescing yellow blobs. They're fluorescing because we're using blue light to shine down on a polished surface. And this illuminates these algal bodies. These are dead, old, 300 million years old algal remains. This distance here from left to right is about 100 microns, by the way. Down at the bottom, we see a different kind of organic matter. This is either woody material or bark. It's from a land plant, different to the algal material. All this stuff can find its way into sediments. Now, that kind of material also has a chemistry, but it's not a simple chemistry, it's a complex chemistry. And I've put a cartoon in the middle here to kind of illustrate how complex that is. We're talking about huge polymers or macromolecules. Methane, one way or another that you find in sedimentary basins, has its origins in this kind of material. It's generated from these bigger molecules. All right, so that's all you need to know. So we're all on common ground, I think. Oh yeah, the size of these molecules are shown at the top here. So how does methane form? I've got to be careful here that I don't prattle on for too long. I'll keep it simple. On this diagram, we have a profile through a sedimentary column. On the left-hand side, you'll see a depth scale from the very top, which is where the ocean water or lake water meets the sediment surface. We then go down through millimeters, centimeters, meters, down to 10 kilometers. And we pass through the realms where biological activity occurs strongly, down into where geological processes are more important. This cartoon that I'm showing first, this refers to the biogeneration of methane. What happens in young sediments is that organic matter, which is deposited from leaves or algae or even dead bacteria, these things are actually buried, and some of that material actually survives and goes down into the geosystem, but some of it is actually degraded here by chain reactions. What we have here are groups of organisms that break down complex polymers into smaller molecules, step by step, and the final product here is methane. The way they do that in detail is not relevant today, but just be informed that this is all done without free oxygen. It's done using these inorganics as electron acceptors, as they're called. So this is the formation of biogenic methane. Let's just wipe that out for a minute. What happens to the organic matter that goes down into these great depths? Here we have our same cartoon again that I showed earlier. Clearly, we're talking about temperatures which are getting higher and higher. We're talking about increases of 30 degrees per kilometer, so it gets pretty hot by the time you're down at 5 or 6 kilometers. And here, then these big organic molecules break down under the influence of temperature and time. They generate hydrocarbons, as shown on the right. Those hydrocarbons are of interest to industry. Clearly, petroleum is important. And the way those hydrocarbons can be found is as follows. The hydrocarbons can either remain where they're generated. We can look there for gas, or the gas can escape and it goes up. Forget about the details here. It goes up into the shallow layers. It can actually be destroyed by different types of organisms here. Methanotrophs actually eat methane and make carbon dioxide. So this is the full cycle, the methane cycle. What we're going to look at today very briefly then is natural gas. We're not going to talk much about biogas. We're going to talk about thermal gas, this deep stuff. All right. So, long introduction, but we're on the same level now, hopefully. So, peddling the methane cycle. There are various targets if we're peddling the methane cycle. And I've lumped those into two groups, the earth scientists and the social scientists. By earth scientists, I'm talking about academia and industry. And by social scientists, I'm talking about the political sphere and the general public. We have to be active in both these areas. Maarten was good in dealing with both these sets of people. Let's begin with the earth science part. Process understanding is the topic here. Now, if you're an academic, you want to study processes related to methane formation, methane migration, methane destruction. And there are four elements that are important. Where does the gas come from? What kind of reservoir do we have in order to trap gas? Is there a seal to keep that gas in the reservoir? And are there geological structures that may allow commercial accumulations to form? As scientists, we're interested in how and when those processes take place, the chemical, the physical, the biological processes. Industry is interested in the bottom line, the cash, right? It wants to find that gas and sell it to make money. So can we really work with industry if we want to be free scientists? A lot of people say, oh, don't work with industry, you'll become a slave of industry. That's not my experience. On the contrary, what we've found is that industry is more than willing to provide data, more than willing to provide samples. Imagine having to pay for finding samples from 6 kilometers depth. You couldn't do it. They pay money to train our students. They allow us to publish everything. And for their part, they then translate our findings into practical terms. So it's kind of a symbiotic relationship if it's done well. You've got to have a contract, an open contract, and it's totally transparent. It works really well. Sounds like a bit like I'm preaching here, but it works well for us. Here's just one example of the work that we've done jointly with South African scientists. This is a joint project with PASA, the Petroleum Agency. It's 15 years old now, but it's interesting, I think, for the topic today. We're in the Orange Basin, and we're looking at conventional petroleum systems, and in particular, leakage. Here we have the area. This is where the Orange Basin is. And this is a profile from west to east, from up towards the coast. All these different colored layers are geological reflectors that are measured using seismic methods. The source of the gas in this region is the Aptian Albion source, which is highlighted in yellow. It's this blue layer. If you look at this image, I think you might be able to see some perturbations in this seismic section. Now I think you can maybe see the perturbations better. They're there. Seismic expression of gas leakage. This is a great place to study methane moving up from deep to shallow. Petroleum companies want to find where it's trapped. But if you're a climate scientist, then you're interested in working out how much of this generated gas gets out into the Earth's atmosphere, because, of course, methane is a strong greenhouse gas. Remember, I mentioned in one of the first slides, there are bacteria hanging around who love to eat methane. So the question, do they get to eat all of the methane before it can escape? Or what? How does this system work? So calculations were made, gas chimneys were identified and mapped. And this study, along with others from other parts of the world, have been published with a view to evaluating petroleum systems as a climate feeder, climate change feeder. I won't now go into any details about more petroleum systems in South Africa, although on the south coast now, it's very exciting to hear there's the opportunity maybe to start producing petroleum down there. Total producing from rifted sediments in the south now. It's very encouraging. I'd like to move straight into the next part of my talk. This is shales. Shales are the source rocks from which gas comes for conventionals. So in my last slide, we were looking at an actin Albion shale that was a source. It had been cooked to the right temperatures to generate gas. But there are some shales which are not only sources, they're also reservoirs. And these reservoirs then are termed unconventionals. On the right, we have a picture of a cliff in Dorset in the UK. This is the Kimmeridge clay. We're talking about 25 meters section here. These are shales, fairly boring to look at actually. But black shales like this, these are the ones we're interested in. This is a core taken through a United States shale sequence, and there are actually gas bubbles coming out of the core. In this case, it's thermogenic gas. It's probably from the Barnett Shale from Texas. If this core had come from the Antrim Shale, further north in the United States, then biogenic gas is actually trapped in those shales. So up till 2000, there was no interest in looking for hydrocarbons in shales because it was technically impossible to get the gas out. That's because the gas is found in very, very small pores. Shown in this picture on the left, we see very tiny pores within organic matter. The organic matter that actually generated the gas has pores, and that's where the gas is stored. Look at the scale. We're talking about nanometer size pores. That's 1 micrometer. Shown on the top right, that's a nanometer, and you see that bacteria, they're about 2 microns in length. A human hair is 30 microns in diameter. So we're talking about really, really small pores. These pores, are they confined to certain layers or are they found throughout shales? This is a profile through the Barnett Shale. All of this profile from top to bottom is Barnett Shale. And here we're plotting different kinds of mineralogy data. We have calcite, quartz, we have a gamma ray log, we have total organic carbon here, some other geochemical data on the right. These profiles show abrupt changes that you see bumps and lumps and jumps. And you can see that the profile is divided into zones. And that's because the shale is heterogeneous. Only in this zone, the second interval, do you actually find gas that's especially abundant. It's found not only in the micron, in the nanometer sized pores, but also within fossils. In this case, you're finding the gas within sponge spicules. So the old spicules and sponges that were living and died at the time, it's the chambers. Bottom left, we see a chamber now, very high magnification. This is where the gas is contained. So this is the place that's most important for an exploration geologist and an engineer. And the reason is that the gas has to be collected or taken out of shales using fracturing or fracking as it's called. The technology of fracking is incredibly high-tech stuff. It's one of going vertically, as shown on the left, vertically down to the shale of interest, and then horizontally for kilometers at a time, using steering mechanisms. This picture here shows that the steering is within the shale. Then water is pumped into those shales, it's fractured, and sand is used to keep the fractures open. And this shows the extent of the fractures in the Barnett Shale. And this blue area shows where the local water aquifers are, much shallower. Now, there's a great deal of controversy about fracking. I'm showing it here because clearly, if you want to be very specific about where you frack, you use geochemistry. For example, this to show where you should be fracking. It's that second layer that's important. All right, let's move on. We'll come to some of the controversy again in a minute. What about shale gas in South Africa? Much earlier in the whole process of seeing if gas is there and if it's wanted, very early in the process, there have been more than 1 million wells drilled and fracked in other parts of the world, mainly in the US. Very few have been drilled here in South Africa, and these are mainly research boreholes. Here down in the south of the Karoo, we see 3 boreholes, research boreholes, that we've had the privilege of working on with Martin, Peter Booth, and his colleagues down where you are in South Africa. Hans Martin Schultz was the leading guy on this. He's the GFZ scientist. He's worked with Naledi Scher and oh shit, forgotten Claire Giel's name, with Claire Giel as well. And these young scientists have been very active in studying shale gas occurrence in these 3 boreholes and in outcrops as well. What came out of it? Well, I can't go into the details, don't have time, but the results have been very encouraging. It's showing that the lower Eka black shales and the upper have significant potential, I think higher than previously thought. Now, the approach that was used in laying out arguments were well received, and Naledi actually received an award, the Jubilee Award of the GSSA in 2018 for the best paper. So congratulations to Naledi for that, and thank you for getting that onto our CVs as well. So we're part of the heroic team that was successful here. Right, let's move on. Right, so now we come to the second topic, social science. I'd like to introduce that by showing an ancient slide that we always show when we talk about these matters, global energy perspectives. World population will increase, more energy is needed. 40% more by 2035 is what we read in the World Energy Outlook from 10 years ago. That might have changed a little bit, but I don't think so. Renewable energy is growing. In fact, it's had quite a boost in the past couple of years, a real significant push, which is good. But our ongoing needs are really relying still on fossil energy. There's a backcloth of global warming that we have to take very, very seriously. Clean energy is important. And of course, when it comes to shales, not in my backyard is a real problem. Nobody wants people fracking in their backyard. So the key challenges, economics versus environment, finding the correct balance, a sustainable solution. That's what we're trying to find worldwide. Now, I just gave you a statistic. I just dragged this out of the detail. India sees 156% growth in its primary energy consumption needs by 2040. That's a huge, huge jump. How is he going to address that? Coal, probably. Gas as well, but coal at the present day is a major energy provider in India. This is now a picture of India, top right. This is coal. It's going to get apparently more important. Go to other countries. Coal is important still. In Germany, coal is important. Oil is important. Very importantly, natural gas plays an important role too. Here we are in South Africa. Go down to bottom left, coal. So there's a big leap in going from these kinds of energy mixes into a sustainable world. Clearly, the path has to be made, and there are those who argue that natural gas is surely a step to be followed in order to build a bridge to renewables. You can't do it in one fell swoop. Gas is clean, gas is good. There are many people who would argue with that. Many people are in disdain of this declaration. Let's just go back to Europe, 2008. The arrival of shale gas, the saviour. Why was it seen as the saviour? Security of supply. Gas was only coming from conventional sources. It was from Russia and Iran and Qatar. People were worried that that might be switched off. The game changer happened. The fracking happened. The EIA in the United States said, let's look around the world. Let's see how abundant shales are. And they came up with this kind of a picture. There's shale everywhere. Nobody really knows to what degree it's technically and economically recoverable, but there's a lot of shale. In terms of organic carbon, not gas, but total carbon, there's 10,000 times much carbon in shales as you have in coal and oil and gas. So it's huge amounts of shale. Right, so this saviour image didn't last long, actually. Quickly switched over to being the villain because of especially this video which came out, Gasland. This is a picture from the Gasland movie, which is showing fracking to be a dangerous practice, basically poisoning everyone and causing earthquakes. Now, this kind of fear technology is the reason why shale gas became the villain. Learned societies in the UK and in Germany, for example, and in Australia, and indeed in South Africa, have said it's safe, but you've got to have good regulations, you've got to have best practices. But that doesn't really, that's not really worked so well, especially in Europe. What you find where I am is that opinions have really won the battle so far. These are opinions that I actually got from a program called QI. This is kind of a program, a popular program, which looks at what people know or what people don't know. Interesting statistics here. 1/3 of Russians believe the sun revolves around the earth. Okay, that's what QI has established. If it's true or not, I don't know. 40% of American adults believe that the world is less than 10,000 years old. Maybe true, I don't know, but these are opinions. Now, facts, all right? Facts are different things. This guy, Daniel Patrick Moynihan, said everyone is entitled to his own opinions, but he's not entitled to his own facts. I show this because, of course, the analogy with shale gas. There are many opinions, but there are only few facts that are important in the shale gas story. And the facts are basically overshadowed. This is Daniel Moynihan's view, facts. Nobody's entitled to his own facts. But we do live in a world where that's not the case anymore. We're living in a world, of course, of influences, viewing planet Earth as we should be getting back to the Garden of Eden type almost. Sorry if I exaggerate. We have people posturing, and we have people cancelling you as an individual if you don't give the right message. So it's kind of a different world to the one that Moynihan grew up in. It's a reality of developing shale gas, and it's one where South Africa is considering developing its shale gas resources with that background. So I was privileged to be involved in, Maarten and I were on this committee, South Africa's technical readiness to support the shale gas industry, 2016. Received full cabinet approval, presented facts, presented what I think is a real technical summary of what should or should not be done. I found Mokhtar suggested I looked at this website here if I wanted an update on the status of South African shale gas. I'd leave you to do that. It looks like an excellent website to look at. There are, of course, activists, and there are those who pointing out that at least some of these activists are getting in the way because they're not using factual argument. But that's not new. That's okay. That's carrying on where others have left off. So with the general public, it's a question of trust then. It's fair enough when people ask, where is this gas that people are talking about, this shale gas? How much of it is there? Are there any real benefits? Do I get a share of these benefits? What are the mineral rights, for example? Very importantly, are there risks? Are we going to get earthquakes? Are the earthquakes going to be like the ones that you see in Indonesia? Or are they going to be like the ones that you see in other parts of the world that are very, very mild? Clearly, we can't ignore the environment. All these are reasonable questions. What we've tried to do in the past, how does academia get involved? Option number one, present the facts. This comes from TNO, which is the Dutch Geological Survey. They said, here are some facts for and against shale gas. Make your own mind up. Over on the right, we had a website where we did the same thing. Was this effective? I don't know. I think it was of interest to some people to actually read these contributions. The second way you can get involved, number two, hands-on. This is the one that I think Maarten was going gung-ho with, not just Maarten, but the other colleagues at NMMU. Monitoring of either industry fracking sites or sites that may become fracking sites. Looking for deep to shallow changes in the ecosystem characteristics. Establishing a base level for the chemistry and physics and the biology of the system. Canada does this, Australia's doing it, the UK has said it's important. But nobody's got into it quite as well, I don't think, as basically in South Africa. The Karoo shale gas baseline study is a fantastic, it looks to me at least like a fantastic way of engaging people, community participation. And here we see Maarten involved in that. So as it's said here in the script, public engagement across the length and breadth of the Eastern Cape have taken place. Series of workshops. Postgrad researchers in the baseline study have been able to present their results. A really good step. What else? Citizen science. Groundwater monitoring projects undertaken here by some of the students. An example is given here, a PhD study entitled Creating Citizen Science for Groundwater Monitoring prior to development or potential development. Excellent idea here. Barry Morkel addressing all of these issues within the public domain by the usual channels, by publications, unbiased presentations of data. So altogether, this is really quite an achievement, I think, so far. So how do we all go forward now in South Africa? It's clear sustainability is the way forward. ઉપયોagship, is this how you pronounce this? This is a fantastic word. Observe the present and consider the past to ponder the future. This is the way forward, not only for, well, in South Africa with that, but the rest of the world balancing these elements of sustainability. There are 4 elements of sustainability, not just one. There's economic efficiency, security of supply. These are really energy issues. Then there's environmental compatibility and societal acceptance. We have to meet present day needs without compromising the ability of future generations to meet their needs. Straightforward stuff. So very briefly now, at the end, towards the end of the talk, what about big research organizations? What are they doing? Ours is, well, I've retired from GFZ, but GFZ is a geoscience research organization. It is not, as far as I know, it does not have fossil energy as a key element as it used to. You have to look beyond that. Sustaining our future is the title of the latest energy program. The energy mix in Germany is shown on the left here, 2018. Renewables, 14%. By 2030, should be 30%. 2050, 60%. The way in which this is being approached, then, what kind of contributions can geoscientists make to this? That's shown on the right of the slide. It involves using the deep subsurface. One thing that's been looked at is geothermal energy. The second thing is using the subsurface to store green energy. And the third is to look for deep raw materials. So that is the way forward for the current research project. Just to look at one of those areas, I mentioned there, storing, how was it worded again? Storing the green energy storage. Here we have a scenario where excess electricity coming from wind power, for example, is transformed into hydrogen. And then with CO2, it's converted catalytically into methane. The methane is then burnt, and the CO2 from that is then put back in the earth. It's a closed system. Now, anybody who's familiar with thermodynamics knows that this is not a very efficient energy provider, but it is a good way of using excess energy that would otherwise not be used. And it's certainly something that is being built upon. Michael Kuhn at GFZ is the guy doing this. Now, second thing, geothermal is big at GFZ, but I thought I'd put this picture in instead. South Africa has its own geothermal perspectives, let's say, the deep mines, the deep gold mines. I noticed that there are publications coming out, white papers on using these deep mines, these spent mines, for generating geothermal energy. This is an old slide that I took from our Inkaba days. And this comes from presentations Maarten was making way back when. I think this is 2008. I could well imagine that these ideas are not just Maarten's. I can imagine these came from science colleagues in South Africa. Clearly, it's coming to fruition at the moment, these invested studies. Right, one final picture here concerning the future. What are the major risks then for GFZ's green program? It's a program that's forward-looking. It is not looking at fossil energy at all. What are the major risks? And you'll see that the major risks are rapidly changing societal needs, perceptions, and political landscapes. So all the facts that are currently being collected for renewables are clearly important. The perceptions are going to be equally important too. So a lot of time is going to be invested by GFZ in doing as Maarten and colleagues have been doing, going out and talking to the people about these new developments. Okay, take-home messages. After all this. First point, earth science. This is where I kicked off, remember. Geoscientific research will continue to improve our understanding of how the methane cycle works, looking at chemistry, physics, and biology. In terms of applied applications of that study, this translates to a more efficient exploration protocols and the securing of raw material supply in the coming years. I believe that this is still valid, still important. The switch to renewables will happen, but making natural gas production and utilization more efficient, that's also a part of the puzzle. Second point, social science, facts versus opinions, now and in the future, a real dilemma. Certainly demonstration programs are vital to test sustainability, all four elements of sustainability, that is. And research organizations or universities can be seen as honest brokers. So that's a very important role to have. Clearly, best practices are of paramount importance. Governance is key. The third point I've not mentioned in the talk, really, but it is linked to points 1 and 2. At least where I am, the teaching of earth science, especially at high school level, is lacking, really. It's the deep earth, the processes of the earth are not really presented in a clear, transparent light. The depths are viewed as kind of an unknown. Geographers are doing the teaching, I think. I think if we don't step up the teaching of earth sciences, this fear factor that's been used by some activists will continue to be exploited. Most people don't know about the subsurface. They don't know what are facts and what's fiction. So anyway, so that's my contribution today. I hope you found it not too preaching, but a bit maybe. Final slide here. Oops, come back, Maarten. Show Maarten again. Maarten was a visionary and a humanitarian. We've lost a great scientist, and I really miss him. I do miss him, in fact. So I wish you well. And for those of you who are working with Maarten's legacy, working on the shale gas of the Karoo, I wish you success. So thank you once again for listening, and I'll now sign off. Bye-bye. Hope to meet you in person one day soon.
Good afternoon, colleagues. It is an honor to be making closing remarks at this memorial lecture of our beloved Professor Maarten de Wit, the founding director of the Earth Stewardship Science Institute and the African Earth Observation Network, who was at Nelson Mandela University. My name is Thandi Mgwebi. I'm the Deputy Vice Chancellor for Research, Innovation and Internationalization at Nelson Mandela University. I knew Professor de Wit firstly and mostly through engagement with his work, and later meeting him through our engagements at the National Research Foundation of South Africa, mainly through his work when he worked in the Department of Science and Innovation NRF-sponsored Inkaba Africa project. I remain in awe about Maarten's contribution. His research, as you know, covered a broad range of areas within earth sciences, including geodynamics, tectonics, and stratigraphy, early earth processes, and the evolution of the Gondwana supercontinent. And this created an extensive body of work that focused on, amongst other things, earth stewardship and transforming sustainable society. It is impressive that Maarten supervised more than 75 PhD students and master students. As detailed in his lecture, Maarten understood the concepts of industry-academia partnership and the involvement of societies in co-creating solutions. Maarten was a champion of sustainability science. It gives me great joy that at the university at the moment, there are conversations in expanding the agenda of sustainability science within the university for further impacting society and making a contribution in the African agenda. But also Maarten recognized the capacity development needs of the continent. His involvement in training students throughout the continent of Africa are commendable. He also understood that addressing environmental challenges and advances in the applications of earth and environmental science are central to the Sustainable Development Goals and other thematic frameworks. In the language of the sustainability development, the planet would be being a central pillar of sustainable development alongside people and prosperity. Significant development trends relevant to many parts of the world include distinct themes with an environmental component. I can mention that the grand challenges of the environment, in fact of environmental stress, challenges of hunger and malnourishment, rapid urbanization and sustainable societies, inequality, energy, and the financial system, all of these require urgent attention. And tackling these will require a need for strengthened policy formation and delivery, ensuring the best available support, science support policy. My challenge to us and to Maarten's colleagues and students is the involvement of earth and environmental scientists. And I'm saying that remains important to explore sustainable development priorities and challenges together, and developing research and innovation capabilities to address them. I would like to thank Brian Horsfield for delivering this lecture, Peddling the Methane Cycle. I thank you, Brian, for the insights, for highlighting the need to co-create solutions with industry, academia, and the public, and also the involvement and participation and contribution that Maarten, yourself, and colleagues have made, highlighting the academic industry process and understanding that leading-edge science can be achieved through co-creation of solutions. It is also interesting that Maarten understood the political sphere and the general and how it can be utilized for best possible solutions. The idea and what you mentioned about misinformation is an important factor and highlights our need to have science communication and engagement as we explore these big challenges and grand challenges. You've mentioned sustainability and the 4 elements involved in sustainability. And you ask a pertinent question: what will the future bring? And this remains a big question for us in academic institutions, in the public sector, the students, the next generation of leaders. I would like to thank you for your contribution. Sincere thanks also goes to ION and through its interim director, Professor Mokhtar Dokuri, Maarten's students and fellow scientists, the Faculty of Science at Nelson Mandela University, and Maarten's colleagues around the world. I want to also thank my Mandela University colleagues, the Vice Chancellor, the executive, and all the colleagues involved in arranging and broadcasting this lecture, allowing us the opportunity to reach out and remember our dear colleague and global scholar. Once again, we send a big thank you to Maarten's family for sharing this giant with us as the scientific community and making it possible for him to influence the next generation of African scholars. With those few words, thank you very much for your attendance, and we hope to have this lecture perhaps next year or once again this year. Thank you.